Hello and welcome back to Functional Analysis. And as always, I want to thank all the nice people that support this channel on Steady or PayPal. We've already reached part 11 in our course and we're still talking about inner products. In particular, today we talk about orthogonality. If you now recall the picture from the last video, you probably remember that only the yellow, the parallel part of y, was important for the inner product. Hence, in an inner product space, it makes sense to say that two vectors are orthogonal. This is simply defined by looking at the inner product, which should be 0. In other words, when we have an inner product, we can use it to define the notion orthogonal. And then, of course, we can also use the common symbol between the two vectors. However, one also uses this symbol for subsets of the vector space X. In this case, one writes u perpendicular to v if x is perpendicular to y for all x in u and y in v. Exactly in this sense, the sets are orthogonal. Now in the next step, for a given set, we can define the so-called orthogonal complement. In this set, we should find all the vectors in X that are orthogonal to all the vectors in U. Therefore, we can write it down as all vectors X in X such that X with U in the inner product is 0 for all U in U. The common notation one uses here is U with an upper index as the perpendicular sign. A good thing you can now check for yourself is that this one is always a subspace in X. Let me point out, you don't need U to be a subspace, U is just a set, but U perp is always a subspace. So please try to prove that with your linear algebra knowledge. In the same way now we can show that the orthogonal complement of the 0 vector is just the whole space. And the other way around, the orthogonal complement of the whole space is the 0 vector. Or to be more precise, it's the set that only contains the 0 vector. Okay, so this is easy to see just by looking at the definition. A little bit more we have to do if we look at subsets. In the case that U is a subset of V, we can look at the orthogonal complements and find that the subset relation is now the other way around. Here I think it's helpful that we write down a proof. For this, let's choose an X from V perp, which means that by definition we have X with V in the inner product is 0 for all V in V. However, because U is a subset of V, we can write down the same thing for all U in U. Hence now by definition again, we have X in U perp. And that's what we wanted to show. That's our set inclusion here. Now the last thing I want to mention here is if you have orthogonal vectors, then you can calculate the norm of x plus y, of course squared, as the sum of the squares of x and y. Of course, don't forget, the norm we have here is the associated norm with the inner product. Now, naturally you recognize that as the Pythagorean theorem. Hence now you know, this holds in general in an abstract way for inner product spaces. If you don't believe me, just try to write down the proof, it's not hard at all. For the end of the video, I want to give you a visualization. If this is a two-dimensional plane in a three-dimensional space, then U perp is a one-dimensional line. This is how you should imagine the relation between U and U perp. The only intersection they have is the 0 vector. Of course, if we have more dimensions than just 3, also the dimensions of the two spaces could be much bigger. However, you might remember an important thing, the two dimensions we have here added should be the dimension of the whole space. So in this case, just 3. Nevertheless, this does not help so much if the surrounding space has an infinite dimension. And this is what we usually have in functional analysis. So later you will see how we deal with this. So maybe as a cliffhanger, in the next video we will show that U perp is always a closed subspace. For showing the subspace property, we just needed linear algebra knowledge. But now also some topological stuff comes in. But as I said, that's something for the next video. Okay, so I hope I see you there. Thanks for listening and have a nice day.